Out there in the quiet corners of the universe lurk objects of immense power. These are black holes, cosmic entities so dense that they warp the fabric of space and time. Not even light, the fastest thing in the cosmos, can escape their grasp. For centuries, black holes were merely theoretical constructs, mathematical curiosities predicted by Einstein's theory of general relativity. But today, we have compelling evidence that these cosmic behemoths are very real. We see their effects on surrounding stars, detect the gravitational waves they emit when they collide, and even have images of their shadows. These images, the first of their kind, captured the world's imagination. They showed us the silhouette of a black hole, a void ringed by a swirling inferno of light and matter. To understand a black hole, we must first understand gravity. Gravity is the force that attracts any two objects with mass. The more massive an object, the stronger its gravitational pull. Think of the sun, a giant ball of gas that holds our entire solar system in its gravitational embrace. Now imagine an object so massive, so incredibly dense, that its gravity becomes inescapable. This is the essence of a black hole. It's a region of space-time where gravity is so strong that nothing, not even light, can escape its pull. The boundary of this region is known as the event horizon, a point of no return. Once something crosses the event horizon, it is forever trapped within the black hole's grasp. The most common way a black hole forms is through the death of a massive star. When a massive star runs out of fuel, gravity wins the battle, and the star collapses in on itself, forming a singularity. Imagine a giant cosmic drain, a region in space where gravity is so strong that it pulls everything inward. The center of a black hole is called the singularity, a point of infinite density. Surrounding the singularity is the event horizon, the boundary beyond which nothing, not even light, can escape. The event horizon isn't a physical barrier, but a region where the curvature of space-time becomes so extreme that all paths lead inward. The size of a black hole is defined by its event horizon, also known as its Schwarzschild radius. This radius is directly proportional to the black hole's mass. The more massive the black hole, the larger its event horizon. Their immense gravity can warp the fabric of space-time, causing time dilation and gravitational lensing. The event horizon is a critical concept in understanding black holes. It's the point of no return, a boundary in space-time where gravity becomes so strong that escape is impossible. Imagine shining a beam of light from inside the event horizon. Instead of traveling outward, the light would be bent inward, pulled relentlessly towards the singularity. An observer falling into a black hole wouldn't feel anything special as they crossed the event horizon. However, an observer watching from a safe distance would see the falling observer appear to slow down and freeze in time at the event horizon. Black holes, despite their reputation as cosmic vacuum cleaners, are not all the same. They come in different sizes, masses, and even spins. The most common type is the stellar mass black hole, formed from the collapse of a single massive
star. Then there are the supermassive black holes, giants lurking at the centers of most galaxies, including our own Milky Way. Some black holes spin rapidly, dragging space-time around them like a whirling tornado.
At the heart of most galaxies, including our own Milky Way, lie supermassive black holes. These are not just larger versions of their stellar mass cousins. They are objects of immense power and influence. Imagine a black hole with a mass millions or even billions of times greater than our Sun. The Milky Way's supermassive black hole, known as Sagittarius A*, is relatively quiet compared to some of its counterparts in other galaxies. Studying supermassive black holes is crucial for understanding galaxy formation and evolution. While black holes themselves are invisible, their immense gravity leaves telltale signs on their surroundings. By observing these signs, astronomers can detect and study these enigmatic objects. One way is by looking for the effects of their powerful gravity on nearby stars and gas. As a black hole pulls in matter, This material forms a swirling disk around it called an accretion disk, emitting intense radiation. Scientists are now using gravitational waves to detect and study black holes. Imagine diving headfirst into a black hole. What would you see? What would you experience? It's a question that has tantalized scientists and science fiction writers alike. As you approach the black hole, the first thing you'd notice is the distortion of light. Stars behind the black hole would appear warped and stretched, their light bent by the intense gravity. As you drew closer, this distortion would become more extreme, creating a swirling halo of light around the black hole's event horizon. Crossing the event horizon itself would be an uneventful experience, at least from your perspective. However, you would be trapped. There's no turning back once you've crossed the event horizon. The gravity inside is so strong that all paths lead inward, toward the singularity at the heart of the black hole. As you ventured deeper into the black hole, things would get increasingly uncomfortable. This is where the concept of spaghettification comes into play. The gravitational pull is stronger at your feet than at your head, stretching your body out like spaghetti. The tidal forces near a black hole are so strong that they would not only stretch you out, but also compress you from the sides. You'd be squeezed and stretched simultaneously, a process that would likely be fatal long before you reach the singularity. One of the most perplexing mysteries surrounding black holes is the information paradox. According to quantum mechanics, information about the state of a particle can never be truly destroyed. However, classical black hole physics suggests that anything that crosses the event horizon is lost forever. This apparent contradiction creates a fundamental problem for our understanding of physics. One possibility is that information is not truly lost inside a black hole, but is somehow encoded on the event horizon itself. Another possibility is that black holes don't truly destroy information, but instead release it back into the universe in a scrambled form. The singularity at the heart of a black hole is perhaps the most mysterious and perplexing aspect of these cosmic objects. It's a point of infinite density, where our current laws of physics break down. General relativity predicts that the singularity is a point of zero volume and infinite curvature. However, most physicists believe that this prediction is incomplete. Some theories propose that the singularity might not be a point at all, but rather a ring or a loop, possibly connecting to other universes or dimensions. The truth is, we simply don't know what lies beyond the singularity. In the 1970s, Stephen Hawking made a groundbreaking discovery that challenged the classical view of black holes as inescapable cosmic prisons. He showed that black holes are not entirely black after all, but emit a faint thermal radiation due to quantum effects near the event horizon. This radiation, now known as Hawking radiation, arises from the creation of virtual particle pairs near the event horizon. According to quantum field theory, empty space is not truly empty, but is teeming with virtual particle pairs that constantly pop into existence and annihilate each other. Near the event horizon of a black hole, one particle in the pair might fall into the black hole while the other escapes into space. The escaping particle carries away some of the black hole's energy, causing the black hole to slowly lose mass over time. This process is incredibly slow for typical astrophysical black holes. A black hole with the mass of our Sun would take longer than the current age of the universe to evaporate completely through Hawking radiation. However, Hawking radiation has profound implications for our understanding of black holes and the information paradox. If black holes can evaporate, what happens to the information they swallowed? Does it disappear from the universe, violating quantum mechanics? Or is it somehow encoded in the Hawking radiation itself? While black holes are often portrayed as destructive forces that devour everything in their path, they also play a crucial role in the evolution of galaxies and the universe as a whole. They act as cosmic recyclers, pulling in matter and energy, and releasing it back into the universe in new and sometimes unexpected ways. As matter falls into a black hole, it forms a swirling accretion disk, heated to millions of degrees by friction and magnetic fields. This hot plasma emits intense radiation across the electromagnetic spectrum, from radio waves to X-rays, making black holes visible to telescopes even though they don't emit light themselves. Moreover, black holes can launch powerful jets of particles and energy that travel vast distances across space. These jets, powered by the black hole's rotation and magnetic fields, can influence star formation, heat up surrounding gas, and even shape the evolution of entire galaxies. In this sense, black holes are not just cosmic vacuum cleaners, but also engines of creation and change, shaping the universe around them in profound ways. They are a testament to the interconnectedness of the cosmos, where death and destruction often pave the way for new beginnings. We've talked about the event horizon, the point of no return. But what happens once you cross that boundary? Imagine yourself falling feet first towards a black hole. The gravitational pull on your feet becomes stronger than on your head. This difference in gravity, called a tidal force, stretches you out. Eventually, you'd be elongated into a thin stream of particles, a process called spaghettification. It highlights the extreme nature of gravity near a black hole. Black holes stretch and distort the very fabric of spacetime itself. Imagine a black hole as a bottomless pit in a trampoline. Anything that gets too close gets stretched and distorted before disappearing into the abyss. At the very heart of a black hole lies the singularity, a point of infinite density and zero volume. Imagine all the mass of a star, or even a galaxy, squeezed into a point smaller than an atom. That's the singularity. It's a place where our current understanding of physics crumbles. It's like trying to divide by zero. The equations just don't work. General relativity, Einstein's masterpiece that describes gravity, predicts the existence of singularities. But it also predicts its own downfall at the singularity. It's like a map that accurately guides you to a point, only to declare, "Here be dragons." The singularity is a place of extremes, where gravity becomes infinitely strong, and space-time curves infinitely. It's a place where time itself might cease to have meaning. What happens at the singularity? Does it mark the end of space and time? Does it lead to other universes or dimensions? These are questions that keep physicists up at night. Some theories suggest that quantum mechanics, the realm of the very small, might play a role in taming the singularity, preventing it from becoming infinitely dense. Others propose that the singularity might be a gateway to a quantum realm, where the very fabric of space-time is woven from quantum threads. Here's a head-scratcher. Quantum mechanics has a strict rule: information cannot be destroyed. Think of it like tearing up a photograph. The information still exists, just scattered. Black holes devour everything, seemingly erasing all information. Does information vanish, violating quantum mechanics? Or is there a cosmic loophole we're missing? This is the information paradox, baffling physicists for decades. Some propose information is encoded on the event horizon. Others suggest black holes release scrambled information. The information paradox challenges our understanding of the universe. In the 1970s, Stephen Hawking threw a cosmic curveball. He proposed that black holes emit faint thermal radiation, now known as Hawking radiation. Near the event horizon, virtual particles appear and annihilate. One particle might get dragged into the black hole, while its partner escapes. The escaping particle reduces the black hole's mass slightly. This process is incredibly slow, taking longer than the universe's age. Hawking radiation suggests black holes slowly evaporate over time. It also adds to the information paradox. What happens to the swallowed information? Though theoretical, Hawking radiation profoundly impacts our understanding of black holes. Black holes are like cosmic riddles wrapped in enigmas. They push the boundaries of our understanding, forcing us to confront the limits of our knowledge. While we've made significant strides in unraveling their secrets, many questions remain unanswered. What lies beyond the event horizon? Does the singularity truly mark the end of space and time as we know it? Could black holes be gateways to other universes or dimensions? These questions tantalize our imaginations and fuel scientific inquiry. Some theories propose that the singularity might not be a point of infinite density, but rather a ring or a loop, potentially connecting to other regions of spacetime. Others suggest that our universe might be a holographic projection of a higher dimensional reality, with black holes offering a glimpse into this deeper cosmic structure. These ideas might sound like science fiction, but they are based on serious theoretical frameworks. They highlight the fact that our journey into the abyss of black holes is far from over. Each discovery raises new questions, urging us to delve deeper into the mysteries of the cosmos. The study of black holes isn't just about understanding these fascinating objects. It's about pushing the boundaries of human knowledge and challenging us to rethink our place in the universe. It's a journey into the unknown, a quest for answers to some of the most fundamental questions about the nature of reality itself. Black holes, despite their reputation as cosmic anchors, aren't always stationary. They can move, sometimes at incredible speeds, through the vast expanse of space. Imagine a black hole, millions of times the mass of our sun, hurtling through a galaxy like a cosmic cannonball. It sounds like science fiction, but it's a reality in our universe. Black holes can be set in motion by various events, such as the gravitational interactions with other massive objects, or the recoil from a powerful explosion during their formation. When a black hole moves, it drags space-time along with it, creating ripples known as gravitational waves. These gravitational waves carry energy and momentum away from the black hole, influencing the motion of other objects in its vicinity. Think of a boat moving through water. It creates ripples that spread outward, affecting the motion of other boats or objects floating on the surface. Observing the motion of black holes can provide valuable insights into their properties, such as their mass and spin. It also helps us understand the dynamics of galaxies and the distribution of matter in the universe. One of the most spectacular events in the universe occurs when two black holes, locked in a gravitational dance, spiral towards each other and eventually collide. Imagine two cosmic whirlpools, their gravitational pull growing stronger and stronger as they draw closer, distorting space-time around them like a funhouse mirror. As the black holes approach, they emit gravitational waves that spread outward at the speed of light, carrying away energy and angular momentum from the system. This loss of energy causes the black holes to spiral closer together, their orbital speed increasing until they eventually merge in a cataclysmic event. The merger itself is incredibly violent, releasing an enormous amount of energy in the form of gravitational waves. This energy is equivalent to converting several times the mass of our sun into pure energy, making it one of the most powerful events in the universe. The detection of gravitational waves from black hole mergers has opened up a new window into the universe, allowing us to study these events in unprecedented detail. It has confirmed Einstein's theory of general relativity in extreme environments and provided new insights into the nature of gravity itself. Fast radio bursts, or FRBs, are one of the most puzzling phenomena in astrophysics. Imagine a sudden burst of radio waves, lasting only a few milliseconds, arriving from a distant galaxy billions of light years away. These bursts are incredibly bright, releasing as much energy in a few milliseconds as our sun does in several days. The origin of FRBs is still a mystery, but some scientists believe that black holes might play a role. One theory suggests that FRBs could be produced by the sudden collapse of highly magnetized neutron stars, the remnants of massive stars that have exploded as supernovae, into black holes. Another possibility is that FRBs are emitted by material falling into supermassive black holes at the centers of galaxies. As material spirals into a black hole, it forms an accretion disk, heated to millions of degrees and threaded by powerful magnetic fields. These conditions could potentially generate the intense bursts of radio waves observed as FRBs. While the exact mechanism behind FRBs remains elusive, their study provides a unique opportunity to probe the extreme environments around black holes and to test our understanding of fundamental physics. Black holes, despite their immense gravity, are not immune to the large-scale expansion of the universe. Imagine the universe as a giant loaf of raisin bread dough rising in the oven. The raisins represent galaxies, and the dough represents the expanding spacetime between them. As the dough rises, the raisins move farther apart from each other, even though they are not moving through the dough itself. Similarly, galaxies are moving apart due to the expansion of spacetime, even though they are not moving through space itself. Black holes, being embedded within galaxies, are also carried along by this expansion. However, the expansion does not affect the size of black holes themselves. The event horizon of a black hole is determined by its mass, and the expansion does not change the mass of a black hole. Understanding the interplay between black holes and the expansion of the universe is crucial for understanding the large-scale structure and evolution of the cosmos. It also has implications for the fate of the universe itself, as the expansion is thought to be accelerating, driven by a mysterious force known as dark energy. The study of black holes is an ongoing journey of discovery, pushing the boundaries of our knowledge and challenging our understanding of the universe. As we develop new technologies and refine our theoretical models, we can look forward to even more exciting discoveries in the future. One promising avenue of research is the Event Horizon Telescope, or EHT, which captured the first-ever image of a black hole's shadow in 2019. The EHT is a global network of radio telescopes that work together to achieve unprecedented resolution, allowing us to study the immediate environment around supermassive black holes. Another exciting development is the advent of gravitational wave astronomy. With observatories like LIGO and Virgo, we can now detect the ripples in spacetime caused by the collisions of black holes and other massive objects, providing a new way to study these events and to test our understanding of gravity. In the coming years, we can expect even more sensitive gravitational wave detectors, both on Earth and in space, which will allow us to detect fainter signals from a wider range of sources, including the mergers of smaller black holes and potentially even the echoes of the Big Bang itself. The future of black hole science is bright with promise, offering a glimpse into the most extreme environments in the universe and challenging us to unravel the deepest mysteries of gravity, space-time, and the nature of reality itself. We've journeyed far, haven't we? From the familiar twinkling of stars in our night sky to the mind-bending depths of black holes, those cosmic maelstroms where gravity reigns supreme, we've peered into the abyss, grappling with concepts that stretch the limits of human comprehension. We've encountered spaghettification, that rather unappetizing consequence of extreme tidal forces, and pondered the singularity, a point where the known laws of physics reach a dead end. Along the way, we've wrestled with the information paradox, that cosmic riddle that questions the very nature of information itself. Does it vanish into oblivion inside a black hole, violating the fundamental tenets of quantum mechanics? Or does it reemerge, scrambled beyond recognition, like a cosmic whisper lost in the vastness of space? We've marveled at the discovery of Hawking radiation, that faint but persistent glow emanating from the event horizon, a testament to the subtle interplay between quantum mechanics and general relativity. And we've witnessed the awe-inspiring collisions of black holes, those cosmic clashes that send ripples through the fabric of space-time, carrying whispers of these cataclysmic events across billions of light years. Black holes, once relegated to the realm of science fiction, have emerged from the shadows of speculation to take their place at the forefront of scientific inquiry. They are no longer mere theoretical constructs. They are real, observable objects that shape the evolution of galaxies and challenge our understanding of the cosmos. They are windows into the extreme, revealing the hidden workings of gravity, the fundamental force that binds the universe together. They are laboratories for testing the limits of our knowledge, pushing us to develop new theories and technologies to unravel their secrets. The study of black holes has already yielded profound insights into the nature of gravity, the evolution of stars and galaxies, and the fundamental laws that govern the universe. But it is a journey that is far from over. Each discovery raises new questions, urging us to delve deeper into the abyss. The quest to understand black holes is a testament to the insatiable curiosity of the human spirit, our relentless drive to explore the unknown and unravel the mysteries of the universe. It takes us to the edge of reality, where physics break down, revealing awe-inspiring wonders. New telescopes will unveil hidden details, revealing black hole secrets with clarity. Advanced simulations will model black hole mergers, providing insights into extreme gravity environments. Perhaps we will crack the information paradox, unlocking secrets beyond the event horizon. The journey into black holes challenges us to expand our minds, question assumptions, and embrace a strange, awe-inspiring universe.